Okay, let's get started. Let's spend a couple minutes talking about the deliverables. I can hear that people are starting to diverge in their solutions for deliverable 7. That's fine. I can also hear that some of you are now realizing the warning that I gave you, which is we're now trying to get matplotlib to do something for which it was not designed to do, right? So that's fine. Whatever solution you come up with is fine for us. I hear that some people have come up with some certain solutions. I'm happy to help facilitate that conversation. So if people have found hacks or ways around matplotlib's failings, send me your solution. I'll put it up on Blackboard. And hopefully on the announcement page there, if you're stuck, there will be a solution that works for you. I heard some people talking about the wireframe hand. That's fine. You don't necessarily need to draw the wireframe hand all the time. The wireframe hand was the simplest thing I could think of to get you started so the user can see what they're doing. If you can come up with something simpler that's more lightweight on matplotlib, that's perfectly fine. Let's see. Some other possible hacks, you can go back in matplotlib to 2D. So again, you can draw the 3D wireframe hand in 2D. And if you do it in the right way, it's still kind of obvious to the user whether leap motion is capturing their gesture or not. You can switch to Pygame. That's fine. Other solutions that people have found. Not yet. Okay.
I would say the wireframe hand is what's causing my issue.
Okay.
I can go around and it will switch states and switch images for me.
Okay.
Just when I introduce, because I'm closing the images,
okay.
when I introduce a new plot, the amend is not working with that plot because of how the variables are set up in functions.
I see. Okay. Okay.
So I was trying to switch it back to object-oriented because I could then just do self.amend.
Okay.
But that was causing other issues.
Okay. Okay. So again, whatever works is fine with us. I mentioned again a few times now this pipes option. So you might want to try and do things in parallel, right? So you want to try and keep your infinite loop running tight, meaning that it's going through that pretty quickly, or else you start to get significant lag. And what the infinite loop can do is use a pipe and start up a separate Python program that draws whatever it is, right? An image, a video, a wireframe, and then it shuts down. But the infinite loop that's capturing data from the user is still running tight. So again, it's up to you what solution you find. Okay. I've also heard that people are dedicating quite a few hours to Deliverable 7. My apologies about that. Deliverable 7 is a bit of a beast. I hope when we talk about Deliverable 8 today, this one's a little bit more lightweight. So hopefully by the end of Deliverable 7, you now sort of have the structure in place where you can switch and draw things based on the internal state of the program. Once you find a solution that works for you on your platform, hopefully you can stick with that for the remainder of the course. Any other questions about Deliverable 7? Okay. Again, if you found workarounds, email them to me. I'll post them to Blackboard as an announcement. Okay, so let's talk about Deliverable 8. So in Deliverable 7, you are adding state to your program, and in Deliverable 8, we're going to be adding data persistence, or in other words, we're going to be adding a database. I've thrown a lot of different concepts at you in the last 7 deliverables, so we're not going to actually set up a database. We're going to do this in a simpler way, which is using Python dictionaries. So you're not going to be setting up a MySQL server and communicating with it. You're going to have an internal database, and all the data that you capture from all of the users that use your system, that data is going to go into the database. Okay, who has worked with Python databases before? One person. Okay, so this will be new for most people. Again, there's a little short tutorial here that you can follow along with. A Python dictionary, as the name implies, is a particular kind of data structure that has 2 parts. There's the key and the description. So obviously, like a dictionary, if you think about a dictionary, the key is the word, and the key and value. Key and values make up dictionaries. For a real dictionary, the key is the word and the value is the description. So keys can be any data structure and values can be any data structure you want. So I'm going to just walk you through deliverable 8 a little bit and show you how this is going to work. So you're going to create a new variable called database, and curly braces always indicate Python Python dictionaries. So in step 1 here, you're creating an empty database. So you've captured no data from your users or Leap Motion. It's simply empty. At the end of your program, you're going to be dumping your database to a file. So when your file quits, just before it quits, it's going to write out this data structure database, which contains all of the data in your program. And then at the beginning of your program, before you enter your infinite loop, you're going to be loading that database back in. So when you shut down your program and start it back up again, the data is going to be persistent because we're just going to shove everything into this database data structure, save it to a file, and read it back in. Right? So that will save us having to get into actual databases and so on. Okay. Okay, we're going to be using dictionaries, and we're going to actually use dictionaries of dictionaries. So we're going to actually create this empty dictionary, and inside that dictionary we're going to store entries, and an entry is made up of a key-value pair. The first key is going to be the name of, let's see here if I can find it. Here we go. The key is going to be the name of the user, and the value associated with that key is another dictionary. And that dictionary contains all the data about this particular user named Josh. So we had initially, this is line 6D here, is printing out this data structure called database. It was originally empty. Now it contains one key value pair. The colon shows the key on the left and the value on the right. The key is a string in this case, the name of the user, and the value in this case is a dictionary. Tell me about this dictionary inside the dictionary. What data does the system have so far on user Josh? Nothing, right? It's an empty dictionary. Okay, so we're creating these dictionaries of dictionaries. After a little while, we now have the database looking like this. Still a dictionary, so the outer curly braces. There are 2 entries, so you can see the entries are separated by a comma. And each entry, again, is a key value pair. So we now have 2 entries at the top level of the database, which are the 2 users that have used my system so far, and we haven't captured anything about them yet. So far, so good? Okay, so in Deliverable 8, we give you a little bit of guidance about starting to build this hierarchical structure. Halfway through Deliverable 8, it's now up to you. You can create any key value pairs you want. What information do you think you're going to be storing in this database, or in this dictionary? Should have named it something else, getting these confused. What data might you want to record about your users?
Progress, lefty, righty.
Progress, okay, so maybe we want to store whether they're a lefty or righty. So maybe inside this database, we make a new entry called righty, and the value, what do you think the value might be? So again, the value can be any data structure we want. True or false, right? So you might have an entry in here where the key is called righty, and the value is a Boolean value, which will just indicate whether they're a righty or lefty. Right? What other information might you want to store? Their accuracy. So how might we record their accuracy in this data structure? What kinds of entries might you want to create? So-
you could do like percent of prediction accuracy or something to that extent.
Percent of prediction accuracy
If
of
you
the
save their
learner.
data versus what you have.
Okay, so the prediction accuracy of them or of the KNN learner?
Your previous Canon learner with their Canon learner?
So there's just one learner underneath, right? And all that learner is doing is grabbing frames of data and outputting whether it's 0 through 9.
Yeah, how much time it takes them to actually sign a number.
How much time it takes them to sign the number, right? So your program knows which digit is being projected, right? So the system is asking the user to sign 3, and the KNN learner is spitting out at every frame a digit, so we can count the number of frames that pass until the KNN learner starts outputting the digit 3, right? So that information would capture how long it takes the user to correctly sign the digit. So how would we encode that in this hierarchical data structure? That's probably some relevant data. Where would it go? So we might want to record how long it takes the user to sign the digit 3, but also how long it took them to sign the digit 4 and 5 and 6 and so on. So we can record global information about the user, like whether they're a lefty or righty. We can record the number of times they've logged in, for example. And then finally, we could start to pull out user records. So in this case, we've got our database. And if we use square brackets and put something inside that square bracket, that means we're requesting the value that's associated with that key. So remember, at the top level of the database, I'll scale back here a little bit, the keys are strings, which are the name of the user. So on line 9A here, I'm putting in a string here requesting all of the information associated with that user. So if username is equal to the string called Josh, then user record will equal the value associated with that key, which in this case is a what data structure? Another dictionary, right? So now I've grabbed the dictionary associated with this string, and it's now being pointed to by user record. And so now I can go into that record and set a new key value pair, which is the number of times that the digit 3 has been attempted. So I see that Josh has logged in. I roll a 10-sided dice, and it comes up 3. So I display the number 3 to the user, and I run this line, which records the fact that Josh has been shown the digit 3 and has been requested to try and sign it, right? So I could add another entry to Josh's user record, which is digit 3 successful, right? Did the KNN learner start to output 3, indicating that the KNN learner is recognizing that Josh is signing digit 3 correctly. Did you have a question?
Like after a certain number of attempts, can we like make the image of that number disappear so they have to do it on their own?
That's a very good question, and that's coming up in deliverable 9 or 10, and that's called scaffolding. So make things easy for the user. We show the digit 3, we show up this picture, and then we see how long it takes them to sign it. If they get better at it, if we record performance accuracy, and on average they get better and better at signing the digit 3, then the next time we pick the number 3 to show to the user, we only show the digit itself and not the image associated with it. We're removing some of the scaffolding and making the task a little bit more challenging. Yes, we will definitely get to that. As I mentioned, you can use any data structure here for the key. So in past years, some people have done the following. So instead of writing out user record, I'll just write UR. You can use the number itself. So this might be a dictionary. initially empty, that contains all the information about how the user has done in terms of the digit 3. Right? So I can store whatever I want in here. I could, for example, then do the following. Once I've created this, the first time that I show the user the digit 3, that's the first attempt. So I create, again, a new dictionary inside this, which is all the information about when the user was exposed to the digit 3 for the first time. If I then create this key value pair, I create this key value pair when the user is shown the digit 3 the second time, and it contains all the information about how well they did during the second presentation of the digit 3. So we can keep creating these deeper and deeper levels of the hierarchy, and you can reference them with square brackets like this, or a comma between them. This also works. I could keep going, so I could say, all right, on the second attempt, during which the user tried to attempt digit 3, how long did it take them to do so? So what was the time or the number of passes through the infinite loop until they started to sign it correctly? So now my key is a string, and my value is going to be what data structure? I'm going to record the number of loops it took until they successfully signed the digit 3. An integer, right? So it took 8 passes through the infinite loop for them to sign the digit 3. So back to your point about progress, right? Let's say this is the hierarchy I start to build up in my database about my users. How would I then query this database or go through this dictionary of dictionaries and compute whether they're making progress or not? What would I be looking for? How are we going to quantify progress in your system?
I mean, how many times they've done it versus how many times it had to go through the loop to be accurate.
How long it took them to do it
Divided by
correctly?
that, right?
We could divide it by that, right? So if we're interested in progress in general, it's probably how quickly they correctly signed the digit over all the digits and over all the presentations of all of those digits. So I could create a nested loop here for I in range 0 through 10. Remember, in Python, it doesn't use the last value here. So I'm going to iterate I from 0 through 9 inclusive. And I'm then going to ask for all the presentations for j in URI, do the following. So let's think about the logic here for a moment. I'm going to iterate over all 10 digits, and in the inner part of this loop, for each value of I, I'm going to pull out j, and j is the key here, right? So if let's say in UR3 here, there have been 2 attempts. So there's 3, 0 and 3, 1. So the user has been shown digit 3 2 times. When I is equal to 3 and we get down here, this for loop is going to realize that there are 2 entries in UR3. So it's going to set j equal to 0 for the first pass through this for loop, and then it's going to set j equal to 1 on the second time through this for loop. Let's say now we iterate, we come back out of the inner loop, we come up here, I is now equal to 4. At this inner for loop looks inside of UR4 and sees that 4 has been presented to the user 3 times. So now j will iterate 0, 1, and 2. So the nice thing about dictionaries is we can just ask for all of the keys that exist. So in this case, there are two entries that exist in UR4, or sorry, 3 entries that exist in UR4 and 2 entries that exist in UR3. So we're going to iterate over all the digits. We're going to iterate over all of the presentations for each of those digits. And we then might, inside here, do some computation using URI, J, and time. So if I reference this, it'll return an integer, which is the amount of time it took the user to correctly sign the ith digit during the jth presentation of that digit. So far, so good? Okay. So again, let's continue this example for a minute. I want to try and estimate user Josh's progress through the system so far. So I'm iterating over all the digits and over all the presentation of those digits. What computation do you think I'm going to be doing in the innermost loop here? What am I going to be looking for? How are we actually going to quantify progress here? Averages. So let's say I know the ASL alphabet already. I come and use your system. The minute it starts up, I start signing everything correctly right off the bat. So mean is not going to be sufficient here.
So you could say the average, their last average, if it's less than or equal to, or I guess if it's less than, then it would be considered progress.
Absolutely, right? So as j iterates from j equals 0, 1, 2, 3, as the number of presentations of a given digit is given, is this number decreasing, right? If it is, that's progress, right? The first time j equals 0, the first time I'm ever shown the digit 3, it takes me a while to figure it out. I eventually get it right. The next time digit 3 is shown to me, I equals 3, j equals 1. I'm a little bit faster, and this integer is a little bit lower, right? So I could perform a computation to see whether I'm getting better or not, and then I might flash something up on the screen to tell the user they're making progress, or maybe they should spend some more time on this particular digit, or what have you. Okay, so that's just a sort of crash course on dictionaries of dictionaries, which is going to store all the information of your system so far across all users, across all digits, and any other information you want about specific events in your system, like the jth presentation of the ith digit. Okay. What you're going to be submitting for deliverable 8 is a walkthrough of your user using the system. So you're going to show a user logging into the system. So this is important. We're going to add some code above the infinite loop that does a little bit of text at the command line. I know I said we're supposed to assume that our users don't speak English. We'll assume that they speak English, at least for the beginning part, which says, please enter your name, your user types in the name, and then it enters into the infinite loop. Once matplotlib starts up, it's very hard to capture text from the command line. So we're going to do all that before the infinite loop. You're going to show somebody logging in. You're going to be showing them doing their thing. You're going to show them stopping the program, starting the program back up again, typing in their username again, so they're logging back into the system, and you're going to show some persistence. So you're going to show when the user logs back in for the second time, before they do anything, there's going to be a visualization to the user showing how many presentations of each of the 10 digits they saw in previous sessions. So this is obviously for your users, but also for us to show us that you're successfully capturing data from one session to the next. And when an existing user logs back in, you've successfully read that database back in, and you're displaying that that data to the screen. Make sense? Okay. A little tricky in this case if you're logging in and trying to film the screen with your phone. We'll give you a little bit of poetic license here. It doesn't have to be a perfect video. Just make sure that we can see these 7 steps in the video. Okay, any other questions about deliverable 8? Okay, if that was a little bit confusing, again, there's a tutorial. You might want to just walk through creating dictionaries of dictionaries before setting out on Deliverable 8. Okay, so back to lecture. Finally, we're starting in on the next theme of the course, which is cognitive psychology. There are going to be 4 lectures in this theme here. We're going to start with the most objective one, which is mental models. And we're going to start moving through different aspects of psychology that are increasingly subjective or hard for neuroscience to get at the moment, but are important for HCI, such as affect, otherwise known as emotion. Okay, we're going to talk a little bit about mental models today. The reading for today is based around a research article that I published about a robot, which you'll see in a moment. So what do robots have to do with HCI? I'm going to show you this robot in a moment, and this robot builds up mental models by interacting with its environment. And the reason why we're going to talk about robots making mental models rather than users making mental models is because one of the nice things about robots is we can break them open and actually see the mental model inside, which we can't do with humans. We can infer that you're building up a mental model because when I show you a new app, you immediately know how to interact with it in the right way because you have a mental model of how apps tend to work. So we're going to look at the nitty-gritty details of how interactions with the physical world lead to mental models. And once you have a mental model, what is it good for? The main thing that a mental model is good for is making predictions. Okay, so the optional reading for today is the actual article itself. This is pretty technical, so I don't expect you to absorb all or any of the article itself. The required reading today is from a colleague of mine who wrote sort of an opinion piece about the article, trying to explain this article for a general audience. So hopefully after today's lecture, you should be able to read What Do Robots Dream Of and understand a little bit about this robot. The title is a play on words. It's a nod to something else. Anybody know what it is? There in the back? Do androids dream of? Electric sheep. Okay, otherwise known as Blade Runner, right? Okay, there's the... Very good. Okay, what do robots dream of? Let's see what robots dream of. Here's the robot. When we first built this robot and turned it on, an undergraduate saw it and turned around when it started flailing around and said, dude, that's the evil starfish. So for better or for worse, that name has stuck. This is the evil starfish here. When I'm going to walk you through an experiment we did with the evil starfish here. What's important about the evil starfish is that when we turn it on, it has little to no understanding of itself. So it's not unlike a human infant who is born in this crazy chaos and gradually starts to build an understanding of self. Where do I end and where does the world begin? And like human babies, the starfish is going to do that by interacting with its environment. How does the robot do that? Well, as you can see, the robot has 4 legs, and it had 4 sensors. We're going to disregard 2 of them here and just focus on the 2 tilt sensors. So whenever the robot moves, it can sense how much it tilts to the left and right, and it can also sense how much it tilts forward and back. So every time the robot pushes against the world, meaning it moves, the world pushes back, and the robot can sense how the world pushed back by seeing how these 2 angles, left and right and forward and back, changed. Okay, so those are its sensors. We tell the robot that it's made up of this main body, this green cube here, and it also has these additional 8 parts, but we don't tell it how those 8 parts are put together. And that's what the robot is going to try and do. So in this little cartoon here are 3 guesses that the robot may make about how it's put together. Each of these 3 guesses is a mental model. So in this case, we're focusing on a particular kind of mental model, which is a self model. The human brain continuously updates and maintains and grows different kinds of mental models about self, mental models about others, mental models about the physical world, mental models about technology, mental models about apps. We're going to focus on just one type for this robot, which is models of self. So far, so good? Okay. Okay, so as I mentioned, the starfish robot here starts its life without a mental model of self. And the first thing we asked it to do is build up an understanding of self. So it's going to start to interact with the world. I will try and actually play this out of PowerPoint here. We'll make it a little easier. Okay, here we go. So the first thing the robot did was to perform this random action. It doesn't know anything about itself. It knows it's made up of these 9 parts. It's been told it has to figure out how it's put together. So in the absence of any knowledge, it just moves randomly. It knows there are these 9 parts, and these 9 parts are connected together with 8 joints. So there's 4 legs. The leg is attached to the main body, and the lower leg is attached to the upper leg. So 2 joints or 2 motors per leg, 4 legs, 4 times 2. It knows it has 8 motors. So it just sends electricity to some of these motors, and the result is that some of them rotate upward and some of them rotate downward, and the main body in this cartoon tilts, in this video here, tilts backwards a little bit. So it knows that when it sends these commands to the 8 motors, the tilt sensors respond in a particular way. So I mentioned that we're talking about mental models here. We're talking about a specific kind of mental models, which are self models. They're also known in neuroscience as forward models. This is important for us because a forward model implies forward in time. When I do something, my model makes a prediction. My mental model makes a prediction about what I'm going to sense in the future, forward in time. When I click on this button in this app, I have a forward model of that app. So I make a prediction about what I'm going to see half a second or a second later when I click that button. If I see something different from what the forward model predicts, I'm either frustrated and I delete the app, or I'm interested because I got a new result that I never got before. I mentioned last time the brain is a prediction machine, and it's a prediction machine in a specific way. The brain is making predictions all the time, and the brain has been wired up to pay attention to things that disagree with our prediction, right? If I send commands to the muscles in my right arm, I predict that I'm going to see my hand in the right side of my visual field. If I send those commands to my muscles and I don't see my hand appear in my right visual field, I'm going to be pretty surprised and I'm going to pay attention to what's happening, right? Okay, so that's a forward model. So as I said, the robot doesn't have a model yet. All it's done is performed this action and recorded this data. Now our robot is going to stop moving for a moment and it's going to run a machine learning algorithm. This one is much more sophisticated than the KNN learner. We're not going to get into the details of this machine learning algorithm. What this machine learning algorithm is doing is iterating over a whole bunch of possible mental models. And for each one of these mental models, or simulations of itself, it's sending electricity to the same 8 motors. Right? So each one of these mental models that you see flipping by, the robot is sending the same motor commands that it did to its physical body. And what is the result of those actions? What happened?
The same tilt.
The same tilt, right? So if you watch carefully, you'll see that the green cube is tilting back, right? So at this point in this robot's lifetime, it's succeeded. It says, okay, I know that in reality I did this, and I got this sensory repercussion. I've now created a whole bunch of forward models that when I do the same thing, when I move slightly forward in time at a moment in the future, I move in the same way. So these models are explaining what I sensed in the real world. How good are these forward models?
In actuality? Not very
In actual reality, from our point of view, not very good. From the point of view of the robot, they're perfect. They predict exactly the sum of this robot's experiences in our world, right? So far, so good. The robot does know, however, that there's a bunch of them. There's a whole bunch of these different mental models that are all perfect. And the robot knows, when I say the robot knows, put the scare quotes around it, it knows that something's funny, right? There's no way that it can be this robot and this robot and this robot and this robot. So it knows it has a bunch of mental models, not just one, but it has a whole bunch that are very different. So if you were this robot, what would you do? Would you keep trying to refine these models?
Do another experiment with your data set?
Absolutely. You do another experiment to add to your data set. So now the robot does this. And now it tilts to the left. It says, okay, I have 2 training instances, right? Remember our discussion about KNN learning. It's a very different machine learning algorithm here, but the same principle. The robot is building up a training set on its own, right? So now it says, okay, I've got these 2 pieces. So now I'm going to take, for example, this mental model, and I'm going to evaluate this mental model twice. Once with the first action I performed, and again with the second action I'm going to perform. And I'm just showing you the second one. You can see that now the main body is tilting to the left, right? So at this point in the experiment, the robot is getting better. It's getting closer to an understanding of itself. You'll notice it says down here the 8th cycle of 16. So we're actually skipped ahead to the 8th experiment, not the second one. So what this robot does is it performs an action with its physical body, stops moving, and tries to improve these forward models using a machine learning algorithm. And the machine learning algorithm is looking for models that explain all of its experiences in the real world. So far, so good? Okay, if you watch carefully, we picked the 8th cycle because our robot has a little bit of a eureka moment here. Okay, at this point in the machine learning algorithm, it stumbled on this forward model, which explained 7 of the 8 experiences it had had so far, but not the 8th one. And you can see why it got 7 out of 8 correct, right? It's almost stumbled on the right answer. A couple more iterations of the machine learning algorithm, and it hits on this, which now explains 8 of the 8 experiments. From our point of view, how good is this model? Not very good, okay? It's not bad. It's got the pieces more or less right. They're bent, right? It's not perfect. This points out another important aspect of a mental model. It doesn't need to be perfect. It only needs to be good enough for whatever we want to do, right? So you get your new,
I'm just
Question?
kind of curious. So what do you want to do once it has a sense of self? Like, do you want it to like jump and?
You'll see we're 1/3 of the way through this video, so I'll show you the latter 2/3 in a moment. Okay. Mental models, forward models don't have to be perfect. You get a new smartphone, it's got yet a new version of the operating system on it. You have to yet again, or I have to do yet again, go in and figure out how to turn off the ringer for new text messages, right? I have a pretty good mental model. I've had 4 Android phones already. I predict it's probably going to be in the settings subdirectory or submenu, not the text submenu. It's good enough. I don't know where exactly it's going to be in the new menu hierarchy, but I kind of know where to go, right? It's good enough. Okay. So we keep going with this experiment. Here's the 16th experiment. And at this point, if you look inside the brain of the robot, this is all you see. It has a whole bunch of slight variations of this model, which for new experiences already predict the right result. So if we were to take this mental model, and the physical robot were to think about performing a new action, it could take that new action and instead of carrying it out using its physical body, it could submit it to this forward model, and the forward model will, or the main body in the forward model will tilt, and that tilt is a prediction forward in time. The forward model says, if you do this, I think you're going to tilt like this. Right? This is a very important skill to have. There's a good reason why all mammals have forward models in the brain. I'm outside and I see that there looks like something like a huge cliff in front of me. I could walk to the edge of the cliff and confirm that, yes, this actually is a cliff. Or I could use my forward model to mentally simulate approaching the cliff and sort of seeing what the situation is there. There's a famous saying in neuroscience that forward models are good because many of them die in our stead, right? Before you actually try out a dangerous action, you might want to consider or mentally simulate that dangerous action and work through what the consequences of that action might be forward in time. Okay, so now the robot is armed with a model of self. The question is, what is this robot supposed to be doing? Well, we've asked the robot to do something pretty simple, which is just move from the left side of the table to the right side of the table. The robot may fall off the table, so before it starts actually thrashing around on the table, it holds still and uses its mental model, its forward model, to find a way to move. So in this experiment, there are actually two machine learning algorithms. One, which you just saw the robot using to build its forward model, or its mental model. In the second machine learning algorithm, the forward model is fixed. The robot says, okay, I know how I'm put together. It's now trying to generate a movement pattern that will get it from the left side of the table to the right side of the table. And in this experiment here, I've skipped to the end of this second machine learning algorithm, and this is what that second machine learning algorithm has found. So the physical robot hasn't even tried this out yet. It just says, I think this might work. My mental model says this will get me from the left side of the table to the right side of the table. So it tells us, the investigators, it says, okay, I'm ready to go. I think I have a plan. We let it try its gate out in reality. You can see why it got nicknamed Evil Starfish. Okay, so up until this point, most robots did not have a forward model. They would thrash around on the table and get better and better and better at whatever we asked them to do. What's the problem with that? Could fall off the table. That's one big problem. What else?
What happens if you ask them to do something else?
What happens if you ask it to do something else? Now it's got to start thrashing all over again and start from scratch. You'll see there's no wires connected here. This robot is running on a battery, and this was a battery back in 2006, which didn't last very long. It doesn't have the energy budget to be doing that. Not only is it dangerous, it's very energy inefficient, and it's not general, right? It can't learn something else. This robot, armed with a forward model, we can ask it to do something. It'll sit quietly. Back in 2006, it would sit quietly for 3 days. Today, it would probably sit quietly for maybe 5 minutes. And then it would do something which may not be perfect, but it would be an approximation of what we want it to do. What I'm showing you here is actually the first half of a longer experiment. So in the second half, which we don't have time to get into, but you can go watch the videos on my website, we pulled a leg off of the robot. So we simulated damage. This was a project that was funded by NASA. NASA's always worried about what happens to their robot probes if the probes break or the rovers break when they get to wherever they're going. The robot's leg breaks. It can't sense the fact that the leg has broken off, but the robot does know that when it performs an action it performed before, now it's getting different sensory repercussions. So it used to have a right leg, and when it performed a certain action, it tilted 40 degrees to the left. Now it no longer has a right leg. It sends motor commands to the motors on the right side of its body, and it doesn't tilt to the left at all. So it knows something has changed. Question?
Like, as it goes through all of this, it takes up memory to do the forward models. Does it delete the forward models that aren't, like, right?
That aren't right, and absolutely it does, right? So when the leg is broken off, the robot knows it's a four-legged robot, and as it gets new experiences that don't match the old ones, the training set is changing, right? We're adding new experiences, and that old forward model, for which it had four legs, cannot explain all the new data. So eventually the machine learning algorithm throws that old one away and adapts it to explain the new experience, and that new forward model is usually a virtual three-legged robot. The robot has figured out that the only explanation of self that explains all of these new experiences is that I'm no longer a four-legged robot, I'm a three-legged robot. The mission, the NASA mission, hasn't changed, however. The mission is still to get from the left side of the table to the right side of the table. We don't care whether you're a four-legged or a one-legged robot. Figure out how to do it. So the robot says, okay, so it stops. It knows it's a three-legged robot, so it starts up that second machine learning algorithm and tries to come up with a new movement pattern that, when supplied to the virtual three-legged robot, gets the virtual three-legged robot from the left side of the table to the right side of the table. When it's done that, it puts up its hand and says, okay, I'm ready to go. And even though it's damaged, it's able to still fulfill the mission. It's a little slower and a little rougher than it was before, but it carries on. Okay, this isn't a course on robotics. I wanted to just use this as an example to explain, first of all, what a forward model is. I do something, and I make a prediction using my model about what sensory repercussion is going to occur forward in time in the future. Where do these models come from? They come through interactions with the world. I do something and I get sensory repercussion. That becomes a training instance in my training set, and I develop forward models that explain that training set. Once I have a good forward model, I can use it to make predictions or mentally rehearse things before having to try them in reality. If I download a new app and I don't have a good forward model or a good mental model, I've got to physically navigate through all the sub-menu items to try and find what I'm looking for. I'm kind of doing it at random, right? I want to use my model to guide me to find the specific function that I'm looking for in the new app. Okay, the evil starfish has taken up all the time for today, so we will start on lecture 11 on Friday. You have Deliverable 7 due tonight along with a quiz. Good luck.